So today we're going to look at tree diagrams, an introduction to counting. So we looked at the weight problem the other day, and we had two of each type of weight, a 1 kilogram weight, 3 kilogram, 9 kilogram, and 27 kilogram weight. And when you had two of each of those types of weights, you realized that you could get 0 kilograms all the way up to 80 kilograms, and you could get every whole number in between 0 and 80 for a total of 81 different weights. And different groups used different methods of getting that there were 81. None of you actually had to sit there and count all of them, but many of you did start counting until you found a pattern, which is an excellent way of doing things. But I want us to think about whether there was actually a faster way to do that. The answer is there was, and I'm not going to say what that way was quite yet. Hopefully you guys will be able to think about that after watching this video. So we're going to start with looking at what a tree diagram is to help us learn how to count. We're going to look at an example. You're going to a party this weekend. You want to look your best. In your closet you have a lot of clothes, but you have narrowed it down to a few items: 5 shirts, 3 shorts, and 2 pairs of shoes. How many different outfits could you wear? Alright, not a very exciting problem, but a good demonstration. So let's list the 5 shirts. We have shirt 1, shirt 2, shirt 3, 4, 5. And if we chose shirt number 1 to wear to the party, we still have 3 choices for our shorts. We could do shorts number 1, shorts number 2, or shorts number 3. If instead of choosing shirt number 1, we chose shirt number 2, we would still have 3 different shorts to choose from: shorts 1, 2, or 3. The same thing for shirt 3, shirt 4, shirt 5. No matter which shirt we choose, we have 3 different shorts to choose from. Moving on to the shoes, if we chose shirt number 1 and shorts number 1, we could choose shoes number 1 or shoes number 2. If we chose shirt number 1 and shorts number 2, we could choose shoes number 1 or shoes number 2. And of course we could keep going with this line of thinking over and over and over again until we have all the branches of our tree. That's why it's called a tree diagram here. All of those branches are sticking out. So how do you read this? What does this mean? Well, if you look at the very top entry there, that means, if you look at that, that means that we had shirt number 1, shorts number 1, and shoes number 1. How do I know that? Because you can follow the path. Starting here at shirt number 1, follow the path to shorts number 1, follow the path to shoes number 1, and there we are. So in order to get to that top one, we had to go shirt 1, shorts 1, shoes 1. So you could do that for each of these. Let's do one other random one. We can start at shirt 2, go down to shorts number 3, go up to shoes number 1. So that one right there means shirt 2, shorts 3, shoes 1. And you could go ahead and write all of these down for every single one, and what you'll find is that there are going to be no repeated combinations. Yeah, shirt 1 is going to show up several times, but with different combinations of shorts and shoes. So we're not going to repeat ourselves ever when we do things this way. So when we do this, we can count up how many different combinations we have just by counting up that last column. And we'll see that there are 30 different possible combinations here. Now, that seems like a really long process, so we want to try to find a shorter way of doing this. So here we go. Here's our tree diagram again, and let's look at it a different way. So if we have shirt number 1, we have 3 shorts to choose from. Shirt number 2, we have 3 shorts to choose from. And the same thing for 3, 4, and 5. No matter which shirt, we have 3 shorts to choose from. In other words, for each of those 5 shirts, there are 3 shorts. Another way to think about it, there are 5 groups of 3. 5 groups of 3 is 5 times 3, which is 15. So there are 15 different shirt-shorts combos because for each of the 5 shirts, there are 3 shorts. So that's without the shoes. Now let's put the shoes in there. So there are 15 shirt-shorts combos. And if we look at that first one of the shirt-shorts combos, we have 2 possible pairs of shoes. If we look at the second of the shirt-shorts combos, we have 2 choices for shoes. Same thing here, here, all the way down. So there we have, for each of the 15 shirt-shorts combos, there are 2 shoes. Another way of looking at it, here we have 15 groups of 2. That 15 came from the 15 shirt-shorts combos, and we have 15 groups of 2, or 15 times 2 is 30. So essentially what we did was 5 times 3, which was our 15, that came from the shirt-shorts combos, and then we multiplied that by 2, because there were 2 pairs of shoes for each of those 15 shirt-shorts combos, to give us 30. Could we have gotten that from the beginning if we had known this shortcut? Yes, because we knew there were 5 shirts, 3 shorts, and 2 shoes. 5 times 3 times 2 is 30. And this, my friends, is the fundamental counting principle, which essentially states if there are A ways of doing something and B ways of doing another thing, then there are A times B ways of performing both actions. So what I want you guys to do is, I don't want you just to memorize the fundamental counting principle. I want you to be able to explain it using tree diagrams. So if there's ever a point when you're solving a problem or doing a project and you use the fundamental counting principle, I'm going to ask you to explain how you know the fundamental counting principle is true. And the way you're going to do that is by drawing a tree diagram. So now you can start thinking about the weight problem again, and we're going to think about it more in class tomorrow.